Welcome to everybody for the second talk of this afternoon. Just before we start, just to remind you that the meeting is being recorded and live streamed. So if you don't wish to be recorded, you need to keep your microphone and camera off and use the chat button for any questions. The live transcript, you may see at the bottom, may be active, but you can toggle this on and off using the live transcript button at the bottom of the screen of your Zoom window. Okay, so it gives me great pleasure this afternoon to introduce Saleh Tanveer to you to give the talk. Saleh is Professor of Mathematics at Ohio State University. He actually started as a maths physics major before going on to a master's in civil engineering and then a PhD in applied maths at Caltech. So he's the author of over 70 refereed papers covering both very applied and very detailed problems of analysis. And they cover areas such as fluid flow, instabilities, vortex sheets, electrostatic fields and ionization, semi-classical analysis, existence and uniqueness of 3D Navier-Stokes equations, solutions of those equations, Safman-Taylor, Hele-Shaw, bubbles and dendritic growth. And it's those latter subjects where Saleh has employed the techniques that are relevant to the program here, employing techniques of asymptotics beyond all orders and resurgence techniques as well. So one of his most recent actual pieces of work, actually, I just noticed, is actually a topical work on the modeling of cholera epidemics. So he has a very diverse, broad interest. So today, Saleh is actually going to speak to us, obviously, on something related to exponential asymptotics. And the title of his talk is Rigorous Exponential Asymptotic Analysis for an Integro-Differential Equation Arising in Viscous Fingering in a Hele-Shaw Cell. So Saleh, over to you.
Thank you very much, Chris. This is work that I'm going to talk about. It's about 18 years old, so it's old work. But as I was looking through the schedule, not many people are talking about this particular topic. It is more on the side of analysis, and I was drawn to this analysis because even after some formal work was done, there were other people who had other things to say, and we thought a mathematical proof would settle this matter. So anyway, so this is work with my ex-student, Shuming She. In fact, most of what I'm saying will be his PhD thesis. For some reason, I'm only, oh, there we go. Okay, so the tools for exponential asymptotic analysis are not very well known. There are problems in water waves, dendritic crystal growth, viscous fingering that involve exponential asymptotics of non-local equations. And until now, almost all work of exponential asymptotics on non-local problems are formal in nature, where non-local contributions are ignored. We present here rigorous results on finger width selection arising in viscous fingering in a Hele-Shaw cell. Those of you who attended the earlier 1995 exponential asymptotics in Newton Institute do know that this was an important problem in the mid-80s and 90s. And so this selection problem remained an open problem since Safman-Taylor's classic experiment in 1958 until the 80s, where it was settled at a formal level, but only rigorously confirmed in 2003. So what is a Hele-Shaw cell? So you take two glass plates, which are parallel to each other with separation B and width 2a, where B is far, far smaller than A. And the length of this cell is even far bigger than A. So imagine that these two ends of the cell, this end that they're facing you on the other side, these are closed, and you let fluid in, the less viscous fluid on this side of the cell, and you push a more viscous fluid through. Now, it was observed in experiment that you get this interface forms a finger, And that's what my talk is about, the formation of steady finger. Now, as far as the equations are concerned, the fluid is highly viscous. So when you use the lubrication approximation and average the flow in the vertical direction, you end up the vertically averaged velocity field being the gradient minus the gradient of a pressure times some constant. And this is precisely the same law that appears in porous media, though that's actually a three-dimensional version of this equation. Nonetheless, you get this Darcy's law, and together with divergence condition, you end up with Laplacian of pressure equals 0. Similar equations arise in dendritic crystal growth when you consider, for instance, the small Peclet number limit. Then you end up the temperature field satisfying Laplace's equation, and the boundary conditions are very similar. So in cell growth, electrochemical potentials, dielectric breakdown, and many other pattern formation problems. So this is this kind of equations arise. In fact, it's as of 2004, Sam Howison has listed something like 500 papers, and he has given up. We don't have any recent updates, but apparently there are many of them, as recently there has been resurgence of growth interest in this area for different reasons. Okay, so the Saffman-Taylor experiment, this is, I show this picture. It's actually a reproduction by Tabeling et al. In '87. The pictures are a bit nicer. So you imagine on the left, I'm not sure if you can see, on the left is the less viscous fluid, and on the right is the more viscous fluid. And if you see the interface right there at the linear stage, and then through a process of finger competition, you have a one big finger which wins out and the others are suppressed. And if you look at that, that's how the finger looks like. And we want to study this finger and the width. It has a well-defined width, which is found in experiment to be close to 1/2 the channel width. Now, Saffman and Taylor, they actually also did a theoretical calculation, and based on the fact that the capillary number was not capillary number, I mean the capillary length was kind of small, it was assumed that surface tension should not play a role in this problem. And when they ignored surface tension, the theory was not able to predict the width of the shape of this finger. So that's became the famous finger selection problem. And let me write down the equations. So you have a domain omega, which is between the channels, scaled here at ±1. And so the domain is omega, is outside the finger, which is forming. And you have Laplace's equation, phi is a scaled pressure. And at the interface, the normal velocity is the same as the normal derivative of the velocity potential. And since it's a free boundary problem, you need an additional boundary condition, which is that the scale pressure is surface tension times curvature. Surface tension here is given by the quantity epsilon square, or scaled surface tension. Everything is non-dimensionalized. Kappa is the curvature. And on the on the walls, channel boundary walls, you have Neumann condition because you don't allow any fluid flow perpendicular to the wall. And at infinity, you have a uniform flow, and that corresponds to phi equal to x plus order 1. And I have scaled the velocity so that the uniform flow at infinity is 1 times x. All right, so this is the equation. This is the equation for the general case when you have unsteady flow. In the case of steady flow, this Vn normal happens to be some constant times cosine of theta, theta being the angle that the normal makes with respect to the x-axis. So how do we handle that problem? Consider there are different people do different formulation. The one that I'm going to use, and I'm going to translate other people's work in terms of this particular formulation. So consider the conformal map that sends the standard domain. The standard domain is the upper half plane, take away the cut from I to I infinity. So take away the cut. So this is the standard domain. And you conformally map that to the domain exterior, to the domain omega, which exterior of the finger, but between the two walls. And that conformal map, it turns out to be a good idea, because in the domain D, you have these two walls, AC and BC, correspond to two sides of the cut. And in the case of a symmetric finger, which is what we'll analyze, then the symmetry corresponds to that points on the upper and lower walls do correspond to two sides of the cut at the same height. And so I wrote here y equal to a as the upper wall. A has been scaled to 1. So this is the Safman, I would call it Zhuravlev-Safman-Taylor solution, because in 1956, earlier than Safman and Taylor, Zhuravlev in the Soviet Union came up with this solution. So here I'm not writing down the expression for phi, because the complex potential phi can be written in terms of elementary function involving logarithm in the work plane. I call it the C is the work plane, which is the upper half plane. Now, the Z naught is the Safman-Taylor solution, exact solution, and then you add in the additional part, which you need when surface tension is not equal to 0. So when you do that, then your equation can be written as the following. Determine the analytic function f. For the function f, the cut disappears, and it has to be analytic in the upper half plane. And C2 in its closure of the upper half plane, that means on the real axis as well, so that for C on the real line, the real part of f is equal to this curvature, imaginary f double prime h prime over this. This happens to be the curvature. Epsilon square is the surface tension, and h corresponds to the zero surface tension Safman-Taylor solution. And notice this h has this expression, a c plus I gamma c squared plus 1 in the denominator, and gamma happens to be this constant related to the finger width. Notice that h is 0 at c equal to minus I omega in the lower half plane, complex plane. And it has poles at c equal to plus minus I. So this h function plays an important role. And it has the parameter which includes the finger width, lambda. When lambda is half, then gamma happens to be 1. And otherwise, if lambda is less than half, then gamma is smaller than 1. And otherwise is bigger than 1. So the problem is to find such a analytic f, and you require that in the far field things go to 0, and that we are looking for solutions which are symmetric about the channel center line. That corresponds to f of minus c is the complex conjugate of f of c. And actually, because of the symmetry, we are looking for symmetric condition. I can actually, the minimal way of formulating this problem, you can only require that you have this equation satisfied for C in R minus union 0. And because of the symmetry of H, this one will be automatically satisfied on the positive real axis if you satisfy on the negative real axis. Anyway, so that's just an observation. Additionally, since Z happens to be a conformal map, Z has to be univalent in this domain, and Z naught is the explicit Saffman-Taylor solution given as a combination of log, and the univalence has to be also required. All right, so McLean and Saffman noticed that you can do a perturbation expansion of this, and this is quite natural in this formulation. You have an epsilon square here. You look at this equation and you find that it looks like I should be able to do an expansion in epsilon square. So this was noted by McLean and Saffman, and there was no restriction on lambda. So what I'm saying is not quite true. You need an additional secondary expansion at infinity, but there is no problem with matching that. And in either case, there is no restriction on lambda. So following work by Kruskal and Segur in a ODE problem, where they showed that if you wanted to find exponentially small terms, what you need to do is hunt down in the complex C-plane points where this expansion becomes formally invalid. And those are the turning points. And those happen in this problem in the analytically continued lower half plane. And by doing that, you actually can do a formal exponential asymptotics, and more on that later. And this was done in the mid-'80s. However, these results were not universally accepted. There were other opinions on this matter. So the formal results are lambda minus half is surface tension to the 2/3 power. Remember, epsilon square is surface tension. So you have a denumerable set of finger solutions marked by in small epsilon limit. All of them tend to 1/2, but at different rates because you have a different set of constants, and only n equal to 1 is found to be linearly stable. Again, an exponential asymptotic calculation that I did in 87B following numerical results by Kessler and Levine. Now, let me go back to the mathematical formulation, how we go about finding this. So remember, this was the equation 1 here, all right? So this is only true on the real line. So what we do is we first form an equation which is valid in the upper half plane. By using Poisson integral formula and the decay rate at infinity, you get, this is the formulation. So G is the analytically continued curvature, and F star is the complex conjugate F on the real axis. So Poisson integral formula gives rise to this expression in the upper half plane. But of course, where the action is in the lower half plane. So if indeed F is analytic, so then on the real line, and you can do analytic continuation, then you collect the residue here. But in collecting the residue, you replace F star by F bar, where F bar is the analytic function that is equal to F star on the real line. So you get this expression. Now, all formal calculations are based on the approximation that I should be negligible and F bar should be negligible. And the reasoning for that is clear because I involves essentially I and I plus have the same formal expression over here, except I is defined for C in the lower half plane, whereas I plus is defined for C in the upper half plane. So they're not the same analytic functions, though they have the same expression. So the point is that I is because of the epsilon square here, so this term should be small. And if indeed there is a solution, it should be small. So that's why this is ignored in all the formal work. And F bar, if F is analytic in the upper half plane, F bar is clearly analytic in the lower half plane. So this F bar has, because of this expression in the upper half plane for F, it follows that F bar in the lower half plane should also be small, all right? So that's the reason what happens is in all the formal work, where the I is ignored and you end up with this formal equation here. Now look at the expression for G. If I set a script G operator, look at that. If I set one of these things to be 0, then it only involves second derivative of capital F and first derivative. So this one ends up being a nonlinear ODE, all right? And it is not so difficult because essentially in the most of the domain near the real axis, F is small. So even though nonlinearity is strong, its effect is not important until you get to the turning point. So that's the basis of formal work. Now, we want to justify everything rigorously. So there is so there are the questions of how do you control I and how do you control F bar, and the other problem is that the eventual result will give a restriction on lambda. So clearly you should not be satisfying this in the entire domain. You should be satisfying it in part of the domain so that you have a solution for any lambda. And then you require some symmetry condition so that you get a restriction on lambda so that the problem has a solution. So that's the plan. So let's define the domain that we need. Let me, the domain, domain is given over here in the shaded region. It's between these two, it's an open connected set between these two upper and lower boundary. And for technical reasons, the upper boundary is chosen this way because it turns out there is a WKB exponent, and the real part of the WKB exponent, we found it easy to prove that the real part of a WKB exponent is actually monotonic on the boundary. And that is the reason you have this strange boundary plane like that, and alpha, there is a lot of leeway in choosing alpha and B. B can be anything less than 1 comma gamma. It should be not just 1, it's the minimum of 1 and gamma. So B can be anything less than that, and alpha is any positive number, all right? And we choose that alpha to be less than B, and so we will, the reason we need to look at functions in this space AK is because, remember, we have to eventually analytically continue the equation in the lower half plane. So we need to set up functions in part of the lower half plane. And that's why we introduce this domain S between the polylines. In particular, S minus will be, I'll refer S minus as the half strip, and that's the part of this domain, shaded domain on the left half plane, all right? So that's S minus. So we'll be satisfying equation in S minus, requires symmetry on the imaginary axis so that it automatically gives the same equation satisfied on S plus. So we define AK to be functions which are analytic and with a weighted norm, and we call AK delta to be the ball of size delta in this norm. And now let's define remember what the classical solution is. I'm rewriting that. We want to determine analytic function F in the upper half plane, that is C2, on its closure, so as to satisfy this curvature condition on the real line. And secondly, f and f prime has to go to 0 at this rate at infinity, and in addition you have the symmetry condition. So this is what is defining a classical solution. There is an additional condition on the equivalence, so let me get rid of that, because it turns out it's quite easy to prove that since Z0 has certain explicit properties, you can show that if I look for solution f, which is f and f prime being reasonably small, then it's quite easy to show that if f and f prime are sufficiently small, which is to be expected because you're looking for a solution close to the Huffman-Taylor solution, then that Z will be automatically univalent. All right. So now comes the theorem. This theorem is geared towards how do I know that if I have a classical solution, I can do an analytic continuation, and that analytic continuation is in the space A0 that I need, A0 or A0 minus. So this theorem addresses that. For small epsilon, any analytic function f, which is a classical solution, in other words, satisfies condition 1 to 3, if I tag along two additional conditions on the algebraic decay rate, if I tag in these additional conditions, then I can show, or we can show, that the analytic function f, the classical solution f, is indeed analytic and belongs to the class A0 delta with f prime in A1 delta. And this delta and delta prime, which you originally required only to be small, but they need not depend on epsilon. At the end of the day, whatever solution there is, delta and delta 1 scale in this manner with surface tension. So you need these two additional assumptions. One is that there is an algebraic decay, and so that if I take c minus 2i to the 2 tau, remember 2i is outside the domain S, so this is indeed a weighted norm not a weighted norm. This is, we are just looking at the real axis, and we're requiring this soup to be delta, and we're requiring delta to be less than 1. As soon as this condition is satisfied, it turns out that you can show that f prime and f double prime belong to this class where delta 1 and delta 2 are finite. However, the assumption B has to say that delta 1 and delta 2 cannot be too large. Delta 1 and epsilon log 1 over epsilon delta 2, each of them have to have small bounds, though those bounds need not depend on epsilon. So these two additional assumptions essentially say that we are looking within the class of classical solutions for which the shape, the slope of the finger is only a minor deviation from the Huffman-Taylor shape, and the curvature is also, curvature can be large but not too large. There is an epsilon dependence which we allow. So delta, in fact, a priori, delta 2 can be large, but epsilon log 1 over epsilon times delta 2 cannot be large. So those are just two technical assumptions which we add, and we will define any problem that satisfies the classical solutions together with these two assumptions. Will, for brevity, we'll dub this as the classical solution. Yeah. So the main theorem says that if you have a classical solution in this sense, then it must be in the analytically continuable and in the class A0 delta. The key step in the proof is the following. What we do is we already know that if it is a classical solution, capital F is analytic in the upper half plane. So we concentrate on the part of S minus, remember this half strip, which is in the lower half plane, all right? And if I can show that, we concentrate on that and we formulate a differential equation of this form. Now, where did this come from? Well, remember I wrote down this equation as the formal analytic continuation. So what we are doing here is, if f is we are not disturbing I is determined completely in terms of an integral involving f on the real line. So if I look at I is known in terms of the classical solution, and it is analytic in the lower half plane. Now, f bar is also known. So what we do is capital F itself is being replaced by small f, which is considered as an unknown. So we look at the left half plane, left half strip, and formulate a differential equation for small f. This is actually a differential equation because the non-local terms can be evaluated based on the classical solution which you assumed exists. And then we formulate an integral equation by using the decay condition and the valuation of this at 0 in terms of the classical solution. And we prove that the solution to this integral equation for small f is actually unique in the class of functions, analytic functions with a weight in the domain D minus. Then what we do is, within the class of continuous function, the same integral equation is shown to have a unique solution on any ray in D minus, including on the boundary of D minus, which is R minus. So therefore, because of the uniqueness, it follows that the classical solution must be this F, and F does belong to A0 minus. Now, if I require the symmetry conditions, additionally, we proved that the small f is analytic on the imaginary axis segment in the lower half plane, which is part of S. And therefore, the symmetry condition implies imaginary f equals 0. And therefore, by Schwartz reflection principle, we are able to say that f not only belongs to the A0 minus, it actually belongs to A0. Right? So that's how we go about proving this problem, proving that any classical solution is actually analytic and belongs to the belongs to A0. All right, now comes the next part, which is there was a paper in Physical Review Letters that claimed that, based on the numerics, that there was a solution for the same equations for a lambda less than 1/2. So this theorem addresses that question. So for any fixed lambda between 0 and 1/2, there exists epsilon naught, so that there can be no classical solution f for any epsilon in 0 to epsilon naught. Now, how do we go about proving that? Well, as I mentioned before, if indeed there is a solution, so you start with if there is so non-existence in some ways is a bit easy to show. If indeed there is a classical solution, we know that f bar and I are analytic a priori. So you actually concentrate on the nonlinear differential equation because you think of I and f bar as given, and you look at the neighborhood of the turning point in the lower half plane. In that neighborhood, you end up with a nonlinear differential equation of this form, and then you basically prove that in the limit of small epsilon, when chi is order 1, v tends to the leading order solution of this equation, which is this. And this has an asymptotic behavior like this for argument of this. In fact, this is the minimal requirement. And this is a well-defined problem, and you can easily show using classical method it has a solution when chi is large enough, and that satisfies this requirement. And on the real chi axis, which corresponds to in the C domain, corresponds to the imaginary axis where we require the symmetry condition, you find the imaginary part of this is the Stokes constant of this problem, S tilde, times this quantity. So therefore, you can only have solution if S tilde is 0. However, the people have calculated this, the Stokes constant, before, and S tilde is not equal to 0. In fact, Ovidiu, Rodica, and Matt Kohut, one of their students, undergraduate students in 2004, proved that indeed S tilde is not equal to 0. And this implies that violation of symmetry condition, and therefore that you could not have a solution when lambda is between 0 and 1/2. All right. Now comes the question of, let me see how I'm doing with time. Not too well, but now comes the question of existence, and this is a bit tricky here. So we consider only the case when lambda is actually, it should be a half open interval. It includes 1/2 to lambda m. So lambda m is some number, so that lambda minus m minus half is small, but need not depend on epsilon. So this is just for simplicity, we restricted to this case. All right, so now the big problem again is that we have this integro-differential equation. Now remember, the integro-differential equation is not expected to have any solution if I pose it, unless I relax the symmetry condition. All right, so when you relax the symmetry condition, you can pose it as a problem on the left half strip, which is S minus. You can pose it as a problem in S minus. However, when you want to impose the symmetry condition, you have to go back on the part of the imaginary axis segment on the lower half plane where you have to require imaginary f equals 0. If you relax the symmetry condition in a naive way, these two guys, I and f bar, becomes unacceptably singular. So this is a major problem. So how do we formulate what we call a weak problem, which always has a solution for any lambda in the left strip, which is S minus? How do we make sure we formulate it in such a way that this I and f bar, or a modified I and f bar that we find, that these are controlled when you know the solution in the left half strip? So for that purpose, there is some gymnastics necessary. One is the following. We introduce this polyline R0 consists of R0 minus, which is a line at an angle, and R0 plus, and R2 minus and R2 plus. These are R0 and R2 at infinity have a slight angle between them. The details do not matter what the angles are. The point is that this R0, polyline R0 and R2 are outside the domain S, whereas R1, which is R1 minus R1 plus, this is inside the domain. And however, if I take the conjugate domain of S, you have to make sure that the conjugate domain of S, if I remember, this is the real axis over here. Real axis is shown somewhere here. I alpha is positive. So therefore, we have to choose these numbers I alpha so that R0 and R2 each of them are in the complex conjugate domain. In other words, if I take the reflection of S about the real axis, that must contain R0 and R2. So what we do is, using this R0, we actually define F minus. F minus is an analytic function below R0, all right? It's an analytic function. It's basically Cauchy integral formula. It's this part, I will explain this part later, this additional part. If I don't care about writing this additional part, it's just it's F bar of T minus C. That's on R0. However, this involves the bar function based on evaluation in SS. But since we want to do a weak problem, the problem is only defined in S minus. And therefore, what we do is we use the expected symmetry so that you only need evaluation on the left half plane of F so as to be able to calculate this F minus. In the case when symmetry condition is satisfied, this F minus will come out to be exactly the F bar. In a similar way, we define these two functions, F plus. F plus is based on R1, all right? F plus is basically the contour integration of F of T minus C dt on R1. However, since the F will only be determined on the left half plane, so we use the expected symmetry about the imaginary axis and end up with a formulation on F plus. Now, if you don't have expected symmetry, if you don't satisfy the symmetry condition, then of course this integral will be singular on the imaginary axis because they will not agree with each other on the imaginary axis. So that's the point. The point is that F plus is not well behaved on the imaginary axis where R1 intersects the imaginary axis. However, F plus is never used. It's used in a limited way. F hat is basically the same equation as what we had over here. Remember, I mentioned at the beginning, F satisfies this equation. This is the equation in the upper half plane. So what we do is we used F minus and F plus. F star is replaced by F minus and F by F plus, and we move this R, we deform this contour and end up getting a function F plus, which is F hat, which is well defined and will agree with F if indeed the function that we are looking for is analytic in the upper half plane and satisfies those equations. All right. So these are and then you define I, you replace the integral I by I2. Now I2 involves, instead of F and F bar, it involves F plus and F minus. So after all this, you end up with a differential equation with an equation of this kind, where I is replaced by I2 and F is replaced by F minus. And the important point is that by doing that, remember R2 is outside the domain. So whatever discontinuity you have for this integrand does not affect the analyticity of I2 in the domain S. Similarly, F minus is also not affected by if the symmetry condition is not satisfied. On the other hand, if the symmetry conditions are satisfied, then F plus is the same as F, and the same as F tilde, and I2 is the same as I. So in other words, we ended up with a weak formulation for which the solution will always exist, and it's only when you satisfy the symmetry condition it's equivalent to the classical problem. So this was a major part, and this gives rise to the following so we took this equation, as I mentioned. We replaced f by f bar, I by I2, and then when we satisfied this equation reads as, after you rewrite it, it reads like this. The important part is that it looks like a much simpler problem, because n, despite its massive complexity, except near the turning point, n is small, because remember, f prime we can show that this is small, this is completely controlled by f in the domain S minus. So this is, each term is small except near the turning point where h is 0, and so what happens is you can actually use the WKB solution of this to form a neighboring operator like this, where the WKB solution that you got is an exact solution to this second order differential equation. And you end up getting a contraction, end up getting an integral equation for which you can show that you have a solution in the left half strip S minus. So this defines the weak problem. And we have a theorem that if f solves the weak problem as A0, in addition to symmetry, then indeed this is true if and only if f is a classical solution. Moreover, for any lambda in 0, 1, the weak problem has a unique solution in A0 minus. In other words, you always have a solution in the half strip, and this is not one way. It's easy to show that if the original problem you have will be a solution to the weak problem, but the other way is a bit more difficult, because remember, when you look for a solution in a strip, you also have to show that that solution, when it satisfies this integral equation, is automatically analytic in the upper half plane, so that it is indeed a classical solution. So that part was the hardest part in this theorem, and let me not give the details there. The next part, since I'm not doing too well on time, so next part is, what do you do next? So what we do is similar to what we did before. Once you have the solution of the weak problem, then you want to go near the turning point, which is minus I omega. And the reason we choose lambda m minus half to be small is we wanted the turning point gamma to be close to 1, so we do not have to do a secondary analysis near minus I. Once you do that, you end up with a nonlinear equation once more, but this is more of a routine nature, because we have seen this kind of thing happening at least at the formal level. It's not too hard to prove that you have a differential equation of this kind, and you have a eigenparameter lambda, which is actually the restriction on lambda. So this A has to be a particular number. So that's the bottom line, in order that the symmetry condition is satisfied. So you basically look at this differential equation, you prove that when epsilon is small, in other words, surface tension is small, the behavior of the solution is this leading order nonlinear equation. With some change of variable, you end up with getting this equation. And then it's a Stokes constant problem. You want the Stokes constant to be 0 on the real axis, which in the original domain corresponds to C on the imaginary axis. So if you want the original variable was f. If you want imaginary f to be 0, then you need imaginary g on the real axis to be 0. And you can prove that that happens if and only if this shouldn't be equal. This is asymptotic. You can prove that that we proved that indeed imaginary G cannot be zero, is zero if and only if S tilde of A is zero. In other words, Stokes constant is zero. And this problem, therefore, boils down to calculating Stokes constant of a nonlinear ODE and finding values of A tilde for which the Stokes constant is zero. So the following theorem is the selection theorem, which says that if lambda is between a half and lambda m is a number bigger than half, but cannot be too large, that lambda m minus half is small, and delta one are the sizes of f and f prime in the norm that we introduced. That if these are small, then the following statements are true. If beta 0 happens to be one of these a n tilde where the Stokes constant is 0 and the derivative of the Stokes constant is non-zero, then there exists an analytic function so that for sufficiently small surface tension, you have the following selection result. And if lambda does not satisfy this condition, if S of A tilde is not equal to 0, A tilde happens to be related to A, which happens to be related to lambda. So if lambda is not one of those magic values, which makes A tilde to be equal to A tilde n, then you don't have any solution for sufficiently small epsilon. And there are some loose ends here which haven't been proved, namely that justification of the Stokes constant being 0, though they have been numerically calculated, they can be proved along the similar lines as Costin et al., but it hasn't been done. The proof of the selection, okay, so that will be the essentially what I have to say. And let me now conclude. What we did was we proved analyticity of classical solution that approach Saffman-Taylor problem and satisfy some auxiliary conditions. It was confirmed that when lambda is between 0 and a half, there can be no finger solution, in contradiction to claims in literature. By relaxing symmetry condition, for a weak problem is formulated for which solution exists in A0 minus. A0 minus is a class of analytic function in the left half strip. And in the weak problem device, non-local terms are completely controlled by F in this A0 minus. You do not need F to be analytic in the upper half plane. You only need F to be analytic in A0 minus. Then nonlinearity is small, except near the turning point, and that affords a WKB treatment, global WKB treatment, where you only have to be careful about the Stokes lines. The weak problem is equivalent to the classical problem when symmetry conditions are imposed. So this is the big part. And what's important to realize is you're only requiring F to satisfy some equation in a half strip problem as soon as you impose a symmetry on a part of the imaginary axis below in the lower half plane, then automatically the function that will come up will be actually analytic in the upper half plane and satisfy all other conditions. Near a turning point, the Stokes constant of the leading order nonlinear problem determines the selection of lambda. There are loose ends, as I mentioned, namely the rigorous justification of zeros of S of A tilde, though they have been calculated numerically by a number of people. There are other open problems, namely how which haven't been done, like selection of fingers with no a priori symmetry assumed. And there are many other problems in this audience. People have spoken about water waves and others involving exponential asymptotics, where where you have these, where you need similar kind of non-local results, and it would be nice to extend this kind of ideas to those problems as well. Thank you.
Thank you very much, Saleh, for a really good and comprehensive talk there. Does anybody have any questions? Anyone? Oh, yes, got two hands up now. Hang on, try and see who those are. Okay, John.
Yeah, I'm afraid a bit orthogonal to most of your talk, but was provoked by the comment at the end. Is the finger in the middle of the channel stable against having a half finger attached to the wall?
Are we talking about stable, not in a time-dependent sense, but whether or not, if you look at asymmetric problem, yeah, so it turns out, and I did this work in '87, the one I did, I looked at the class of non-symmetric finger, and my conclusion was, this was based on formal asymptotics, that as soon as you put in surface tension, then the only solution that survives is the symmetric finger with lambda equal to 1/2 or whatever this law says.
But it's a slightly different question. You could attach half the finger to the wall, right? So the question is whether the finger...
Half a finger to the wall? I don't understand. I mean, I thought you were talking about like doubling the width of the channel and having two fingers rather than one, which would correspond to asymmetric fingers. No, you don't mean that.
No, it's the opposite. It's when you only have half a finger. So say pi/2 contact angle, you stick half a finger on the wall. It strikes me it's more mathematically, that's likely to be more stable than one in the middle of the channel. But I don't know if anybody's ever looked at it.
Oh, I see. Half a finger with 90 degrees.
For example, I mean, you could generalize the problem.
So if you have half a finger, how does it, if I do a reflection, how does it differ from having a complete symmetric finger with twice the width, twice with double the channel width? How does it change mathematically?
It doesn't, except that I mean, that's actually my argument for why it's more stable. Then you're putting one finger in a double width channel, whereas if you did the same with the finger, if you doubled up with the finger in the middle, you'd have two fingers.
Yeah, so if you essentially increase your A, that has the effect of decreasing epsilon. All right. Because epsilon squared happens to be b squared t over 12 mu a square. So if you increase A, you have the effect of effectively decreasing surface tension.
Right, so the thinner ones are more stable.
Yeah.
Why don't you get multiple fingers, generically get multiple fingers in the channel there?
Why do you get generically multiple fingers? Actually,
why don't you generically get multiple fingers? Because they would all have strong irregularizing effect.
Yes, that's a good point. That's an interesting question. Yeah, let's talk about it later.
Yeah, no, it's always puzzled me. Thank you, Saleh. Nice talk.
Sure, thank you.
Okay, Abhijit.
Well, actually, this answered my questions too, really. So,
okay, good. Okay, thank you. Okay, maybe we'll stop recording now.